All right. Welcome to Lecture 31. It's Chapter 7, Part 5. We're going to talk about the strengths of different bonds. Okay. So it is good, it's valuable, it's important to be able to differentiate different bonds, be able to compare their strengths. So we're going to do so for both covalent and ionic bonds. Okay. These have very different sorts of considerations in terms of how strong the bonds are and how we compare different bond strengths. So with covalent bonds, we measure the strength of a bond by looking at how much energy it takes to break it. Okay, so how much it takes to pull it apart. And there are various ways you can do this, but it all boils down to just ripping molecules to shreds. Okay? So we get tables of bond strengths, CH, CO, 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 and we can compare these things. Like for example, the carbon-hydrogen bond is 415 kilojoules per mole. Okay? That's how much energy it takes to break a carbon-hydrogen bond. Except that that is an average. Okay? It's an average. It's not, always going to be the same for every single bond. Okay? Different bonds are going to have slightly different strengths because, different molecules see different environments. Okay? So the carbon-hydrogen bond in methane is going to be slightly different from the carbon-hydrogen bond in ethane. Because, they're different molecules. The bonds see different environments, so they're going to respond in different ways. So when you see in a table like this, for bond strengths, just recognize that we're looking at averages. We're looking at, just sort of the typical carbon-hydrogen bond, or the typical carbon-oxygen single bond, or the typical carbon-oxygen double bond. Realize that it's an estimate. It's a pretty good estimate. It's not a great estimate. But because we can get that estimate, we can use one of those tables to calculate an enthalpy of reaction. Something we've already done. In the past, we have done things like products minus reactants. Looking at delta H of formation for the products, the delta H of formation of the reactants. You can also do that by looking at bonds. So, for example, methane plus oxygen yields CO2 plus H2O. Now it's balanced. Before it wasn't. All right, so what you do is you look at the amount of energy you have to put in and the amount of energy you're going to get out. In other words, what kind of bonds do you have to break? You're breaking bonds on this side, and you're putting bonds together on this side, so the bonds you break versus the bonds you form. So over here, you have carbon-hydrogen bonds. You have 4 carbon-hydrogen single bonds. Here you have 2 oxygen-oxygen double bonds. Over here you have 2 carbon-oxygen double bonds and 4 hydrogen-oxygen single bonds. Because, molecule of water, each one has 2 of those bonds and there are 2 of those molecules. So, the delta H for this reaction is delta H reaction is equal to just the sum of the bonds broken minus the sum of the bonds formed. Okay. And that's because of the way we record these bond enthalpies, broken minus formed. So, like I already said, for carbon-hydrogen, it's 415 times 4 plus oxygen-oxygen double bond is 498, and there are 2 of them. And then you subtract the bonds that are formed, so the 2 carbon-oxygen double bonds 741 kilojoules per mole. There are two of those. And now we have our hydrogen-oxygen single bonds. 464, and there are 4 of them. Which gives us, for this particular reaction, an enthalpy of reaction of negative 682 kilojoules per mole. Now, the actual enthalpy of combustion for methane is negative 882 kilojoules per mole. So, as we can see, that's a pretty big discrepancy. That's a lot of energy difference, actually. So, you always have to take this sort of enthalpy with a grain of salt. Okay? It's not a great estimate. I mean, it's not terrible, but it's not great. Okay? And just to remind you, it's broken minus formed. So that's for individual bond enthalpies. Okay? When you're looking at enthalpies of formation, it's products minus reactants. For bond enthalpies, it's broken minus formed. Now, in general, not looking at numbers, just looking at trends, we can make some general statements. A longer bond is a weaker bond. Okay? Because, a bond is the thing holding two atoms together. So if they're being held together more strongly, they're going to be held more closely together. Okay? This one hopefully should, seem nice and clear. If you have more bonds, it's a stronger bond. Okay? So a carbon-carbon bond is going to be weaker than a carbon-carbon double bond. It's going to be weaker than a carbon-carbon triple bond. Okay? Once again, they're held more tightly, they're more closely bound, and because, this is the strongest, it's also going to be the shortest. Okay? They're going to be held much more closely together. And for any particular bond, okay, say A bound to X, some species, and then you're comparing, a group on the periodic table. So you could be comparing the halogens, fluorine, chlorine, bromine, iodine, and so on. Or you could be comparing the pnictogens, nitrogen, phosphorus, arsenic, and so on. We're comparing some element bound to a group, and we can compare the different kinds of bonds. And so the bond gets weaker as it goes down the group, stronger as it goes up the group. Just because the heavier elements, their valence electrons are further away from their nucleus. It changes the energy levels of their bonds and just makes them have slightly weaker bonds in general. All right, so those are the 3 trends you need to know. Well, really, they're just 2 trends regarding bond strength, and then a trend regarding, bond length as it relates to bond strength. Now, something to note is that resonance plays a role in both of these. So it really shows up for more bonds being stronger or fewer bonds being weaker. So, for example, looking at carbonate and carbonite, well, and then carbon dioxide. Okay. Okay. Okay, so carbon dioxide, you have a carbon-oxygen double bond. Okay, it's nice and straightforward. Whereas here you have a 1.5 bond because of resonance. And here you have a 1.33 bond because of resonance. Okay. That means that the carbon dioxide bond is the strongest bond, the carbonate bond is the weakest bond. Okay. So, strongest and weakest. Okay. Not only that, but carbonate has the longest bond, and carbon dioxide has the shortest bond of this particular group. Well, the same thing would be true for, nitric oxide and nitrite and nitrate. Just, more bonds is a stronger bond, regardless of what elements you have involved. So, but you have to be careful about trying to compare between different elements, okay? Because, here we have nitrogen, down here we have carbon. Okay. You can't compare those two in the same way as you could down here, because nitrogen and carbon aren't in the same group. Okay, so it gets more complicated when you go from one group to another group. So the only way you'd know which one is stronger there, you'd basically look it up on a bond table. Let's look at ionic bonds. Now, ionic bonds are more complicated because you don't have individual bonds, okay? Now, like with a covalent bond, you have an atom, and then you have the bond between them. You don't have that with ionic, okay? With ionic bonds, you have an ion that's surrounded by other ions of opposite charge. Each of those is surrounded by ions of opposite charge, which are surrounded by ions, which are surrounded by ions, and so on. Okay? So the ionic bond is really the entire structure of the ionic compound, this huge dispersed thing where you have positive and negative charges all throughout the crystal. But we can still come up with, a good rule of thumb. Okay? And that's because the bond strength is going to be based upon the force between the ions. Oops. All right. So the force between the ions, negative k q1 q2 over r squared. This is just a proportionality thing. Don't worry about k. It's just, in order to get the units right, going from charge over distance to newtons, right? So Q1 and Q2 are charges, the charges of the two ions involved, and r squared is the distance from nucleus to nucleus. Okay, so from center to center. Okay, so just R, and then a different R, and then probably the same R, and then another R, and so on. All right. So what you do is you just calculate the force on that atom from the other guys nearby, and that gets you the energy, which is nicely related. All right. So what does this tell us? It tells us that increasing charge increases force. Okay, so the more highly charged the ions, the greater the force between them. Okay, you double the charge on one of the ions, you're doubling the strength of that force. Okay, so going from, say, lithium to beryllium, okay, that's 1 plus and 2 plus. You're doubling the charge. Beryllium, you should expect to have a more strongly bound crystal. And this right here tells us that bigger ion equals weaker bond, okay, or weaker force. Okay? Because you're dividing by a bigger number, you're going to get a smaller number. Okay? So the force is going to go down as the ions get bigger. And that really has a big impact as you go down, the periodic table. Okay? Because the ions get much, much bigger. So a bigger ion is a weaker bond. Generally speaking, increasing charge is easier to compare just because those go in discrete steps, and you don't really double size just by going down one row on the periodic table. And this is the sort of thing we can see when we actually look at compounds, okay? Such that, okay, we can compare lithium fluoride to, let's keep it simple, beryllium fluoride versus potassium fluoride and calcium fluoride. And what we would compare would be melting points. Oops. Melting points. Because when you think about it, you're trying to melt a crystal, you're trying to get all those ions free, you're trying to break the ionic bond throughout the structure. So the stronger the bond, the higher the melting point is going to be. Now, things being what they are, beryllium fluoride, we have to leave it out of this particular example because it's actually more covalent. It's just ish. It's just kind of weird that way. But we can easily compare, lithium fluoride and potassium fluoride, and we can easily compare potassium fluoride and calcium fluoride. The reason we can do that is because lithium and potassium, they have the same charge, 1 plus, but different sizes, because potassium is bigger, okay? Bigger. So we should expect potassium fluoride to have a weaker bond than lithium fluoride. Now, calcium has a 2 plus charge, and potassium has a 1 plus charge, so we should expect calcium, they're about the same size, we should expect calcium to have a stronger bond. Now, lithium fluoride has a melting point of about 845 degrees Celsius. Potassium fluoride is actually about 858 degrees Celsius. Calcium fluoride is 1418 degrees Celsius. So calcium fluoride definitely has a stronger bond. But lithium and potassium are about the same. So what's happening there? I guess lithium fluoride, still slightly weird, sort of like beryllium fluoride. But this definitely matches the trend. Okay, double the charge, much stronger bond. You can always count on that to be a good predictor of relative bond strength. So, when it comes right down to it, what sort of bonds can you compare? Ionic versus covalent is right out. Okay, they are just wildly different kinds of bonds. The bond strengths, you're looking at very, very different kinds of things. So you just can't compare those two, not really. But ionic versus ionic, not great. Okay, just because crystals, ionic compounds, can have very, very different structures, which will affect the way they, that'll affect their bond strength. So you can make comparisons, but it's better for, closely related crystals. So sodium chloride and sodium bromide is a good comparison. Sodium oxide versus sodium sulfide is a good comparison. But sodium chloride versus sodium oxide, not so much, just because they're going to have a very different kind of a crystal structure. So yes, yes, no, no. Okay. And we can see that up here. Something strange was going on with this comparison up top. Now, covalent versus covalent, we can definitely do. Okay? But even then, because we're looking at molecules, and molecules have individual structures, it's a little harder to tell. So there, you have to be able to draw, the Lewis structure. Okay? If you can draw the Lewis structure, then you can compare bond strengths, which means that you still have to be looking at closely related compounds. For example, CO2, CO2 2 minus, CO3 2 minus, all the same kinds of elements involved. Or you could compare hydrogen chloride, hydrogen bromide, hydrogen iodide, for example. All right, and that does it for this section. See you later.